Okay, hello. So we will present you some results on the environmental performance of the Glopack packaging. For this, we relied on the conventional life cycle assessment methodology, but also went beyond that and had a look to, in this case, also plastic waste. First of all, what was the role of UGent in the Glopack? Well, we were focusing on the environmental performance. So in work package 2, we were involved to monitor key process performance indicator, and we also had a look to quantify the potential resource savings and waste reduction that occurs when scaling up the process. But then we are focusing on work package 4. The goal has already been explained before. So we were really working on the evaluation of the environmental sustainability of the innovative packaging concepts. And if we are talking about the environmental sustainability, then if we are talking about the environmental sustainability, then we start from the principle of life cycle thinking. And one method that allows us to meet this challenge or to meet this goal is life cycle assessment, or LCA. And this is a method that allows us to evaluate the environmental performance of a product throughout its full life cycle. What does it mean? If we are talking about the conventional fossil-based plastic packaging, it means we start with raw material extraction. So fossil fuels need to be extracted, then we will manufacture the packaging material, it will be distributed, it will be used, and then the question is what happens afterwards with it. What we are doing is really have a look to each step in the life cycle, what are the resources that were needed, and what are the emissions that occur. In this case, in the Glopack case, we are not talking only on the packaging, but we are also talking on the combined food packaging system. It's always a bit slower. Okay. First of all, if we are talking about the spec food products, what do we consider? Then we can actually see 8 stages in the life cycle. We first of all have the raw material production. So we have packaging that needs to be produced and food ingredients as well. They are both transported to the food company where processing takes place and packing and filling. Afterwards, the spec food product will be distributed, will go to supermarkets where it can be bought by the consumer. At each, you cannot see it maybe because of the light, but at each of these stages, we also can have some losses. So it means losses can take place in terms of food and in terms of plastic packaging. So here we have the end-of-life box as well to treat the food loss and waste, and also to treat the packaging material. What we are going to do is, in this first step, collecting all data. So I was talking about what were the resources needed, what are the emissions that occur. So we really want to collect the data for each of these steps. Today we will focus on this packaging production step. And we can try, first of all, what we do is trying to collect primary data. Primary data is data that is case specific. So that is in collaboration with the partners. Secondary data is helping us to find data in databases, in literature, etc. If we were talking about the packaging material, this has been explained before in a much better way by Helene, but we are focusing on the production of the pellets, which can then be processed into cups and trays, and also actually the production of the intelligent label was under consideration in our innovative packaging. Today, in this presentation, we focus on the production of these pellets, in which we have 3 main steps that we will consider. We have the Glopack HPV production. It was mentioned already, the milled fiber production, that it might have an impact on the environmental impact if this is added. So I can show you the results now. And then we also have the compounding. If active compounds are added, it's also in this compounding stage. First of all, this data collection is not that easy. I think the partners involved noticed this as well. It's also sometimes very time consuming, but we try to do our best, and we were able to construct mass and energy balances. So thanks to the help of the partners. Next to the close collaboration, we also had still some missing data needs for which we relied on other industrial partners and research partners, literature and lifecycle inventory databases. But not all processes are already operational at full scale. So while in this story, we were actually trying to evaluate the full-scale production. So it means that we had to try to scale up, and this was done based on expert knowledge, on validating the results in literature, etc. Further on, we should keep in mind this was like a conservative way of working because later on, if the technology is very established, we might have further improvements. So we have collected all this data, but what does it mean? Because we are still talking, we still want to come to the environmental impact. And then we rely on cause-effective chains. So we start with, I will give the example of the carbon footprint, which is the most well-known, I think. So we start with the emissions. Greenhouse gas emissions will contribute to global warming. So then we have here global warming or carbon footprint. But this is still somewhere at the middle of this cause-effect chain because global warming will result in an increase in the global mean temperature. This might affect the number of diseases, for instance, and in this way affecting human health or ecosystem quality. So that's more at the end of the cause-effect chain. So we call midpoint and endpoint level. Next to carbon footprint at midpoint level, you also can have other categories. Think about eutrophication, acidification, etc. Also, at endpoint level, we are not only trying to protect the human health or ecosystem quality, but also the amount of natural resources. And then we can even aggregate this in one single score. So then this gives us like the traditional way, the carbon footprint. But we can also go a step further and really having a look to the amount of resources that are used in our process. We call this creating a resource footprint. And for this, we have relied on the method C, in which we have a look to the amount of natural resources extracted from the environment. And we have a look to the number of, or the amount of minerals, fossil fuels, etc. that were needed to produce our packaging material. We can express this in one single unit based on thermodynamic principles. This is just still an easy way to complement the traditional LCA, but there are still things missing. Yeah, if we are thinking about the some cause-effect chains, not all environmental impacts are modeled properly. For sure, if we have a look in this case to marine litter and its effect, but this will be presented by Niels in a few slides. If we then come to some results, I focus here first of all on the impact of 1 kilogram pellets, but based on the resource footprint. So what is the amount of resources needed to produce 1 kilogram of pellets? I have distinguished here like the 3 stages: PHPV production, then drying and milling. So it means here the wheat straw is included, and then we have the compounding. It's clear that there is one bar which is the highest, so most resource intensive, and this is the PHPV production. If we have a look to the colors, then it's clear that electricity is taking the highest amount, followed by the nutrients. Drying and milling is having only a very small impact, and then for compounding, it's mainly electricity. Of course, this PHPV production is the new production, so for sure, improvement is possible when it's an established methodology. So this is still showing actually a bad case, let's call it like this. If we then put this a little bit further, so we have a look to 4 options of Glopack pellets. In the first option, we are talking about the fact that we have the first 2 options are including fibers, the 2 others are without fibers. Then it's clear that when we replace part of the fibers by PHPV, we come to a higher impact. So that's already one thing which is clear. And then we still have the second and the 4th option. This is always with active compounds. So these active compounds have actually a lower impact than the PHPV. So that explains the small decrease in the resource footprint. But if we now compare this with pellets on the market, then I've here shown you polypropylene, and here we have polylactic acids. Polypropylene has a higher resource footprint. It's mainly due, which is quite logical, due to the fossil fuels, so this orange color. If we go to PLA, then we see that this is really very similar to the Glopack pellets which were used in the experiments today. What is nice to know is that actually in PLA, a lot of the impact, 37% of the impact is actually due to, in this case, from the database, it was made out of maize grain. So the use of agri-food waste seems to be beneficial in this storyline. And I think I can give now the floor to Niels to say something more on the marine energy aspect.
Thank you. Okay. So first of all, I want to thank the organizers for a second question on the WOOC lab, which introduced a bit the issue with leaching in the marine environment. And also a bit of context here before. So we are now producing about 450 million tons of plastic each year, and it's quite exponential growth. And we have produced more than half of the plastic the last 20 years. And about this plastic produced, 36% is packaging. And what about circularity? Yes, still a huge fraction is directly discarded. We only have about 70% of collection, and recycling represents about 15% for the last numbers. So of course, there is a substantial fraction which is going in the marine environment. And the last estimate reports 11 million tons of plastic each year going in the marine environment, so direct leakages in the marine environment. Or this represents 50 kilos of plastic per meter of coastline worldwide, so it's quite substantial. And the scientific community now consider marine littering as a planetary threat, because of course it's spread at global scale, it's not reversible, and it has a lot of impacts, and a lot of those impacts are not really understood well so far. If we take back the scheme from Lisbeth, in this second part of the presentation, we focus on, in fact, on the emissions, and the idea here is to understand the fate of the plastic waste collected in Europe. So we start from the collection, it's important to keep in mind, and the fate of this plastic waste at the end to finish in the marine environment. So we want to assess the probability of European plastic waste to end in the marine environment. And we developed a kind of model, I would say, based on 3 key parameters: the amount of export of plastic from Europe, second thing, the different waste treatment options, and the last point, which is, I would say, the climatic conditions and the hydrography of the place where the plastic leakages are happening. So, of course, you have the leakage on the terrestrial environment. What is the probability then to finish on the marine environment based on the amount of rivers, precipitation, the wind condition, and so on. So we start here from the plastic waste which is collected in Europe, and at the end, as I said, we want to understand what is the fraction which is going in the marine environment. First of all, we consider the amounts of plastic waste which are exported from Europe based on international trade data. Then, for each importing countries of European plastic waste, and also in Europe, we look at the proportion of the different waste treatment options for plastic. So we have recycling, incineration for energy recovery, landfilling, including incineration, I forgot to say, it also includes composting there, improper disposal, and finally leakage. And for the leakage, we link them with marine litter based on the hydrographic condition and the meteorological condition of the environment. At the end, we found that in Europe, if we collect about 28 million tons of plastic each year, and out of these 28 million tons, based on a model, we find that we have 5,000 tons, about 5,000 tons, which are going as marine litter. So this represents 0.02% of these 28 million tons. Again, I just want to emphasize that we start from plastic waste collection. So why this number is quite low. First, because we have quite a huge amount of plastic waste in Europe which are recycled, incinerated, and landfilled, about more than 90%. And then the exports, mostly to Asia and Turkey, are quite low as well. Only 6% of the plastic waste fraction. And even in this country now, the recycling, incineration, and landfilling is reaching more than 70%. In fact, they've made like huge improvements these last years. So just a reminder, the probability of European plastic waste to finish in marine environment is 0.02% now, so that's the number of tons. So for 1 kilo of packaging, for example, which would be collected in Europe, this would potentially represent 0.2 grams of marine litter. Of course, the model has some limitation. First, we do not consider the different type of material, of plastic material. For example, if you have higher value-added materials, maybe you won't landfill them, but you will have like higher recycling rates. So, and then it does not distinguish between, for example, a compostable plastic material with conventional plastic such as PP. And then also the model starts from the plastic disposal, so really the collection of the plastic, and it does not consider all the fraction of plastic which are directly discarded by the consumer, for example, before being collected. And I just want to finish this section on some insight on degradation of PHBV, because now the result, which is in fact this probability of 0.02%, does not consider, will not provide different results for example, PHBV and PP as an example for conventional plastic, so we will have the same results of amount of plastic leaking to the marine environment. But of course, the accumulation won't be the same. For example, for PHBV now, we know from experimental results that it takes about 1 year to degrade in the marine environment, of course, under lab conditions, while for a conventional plastic, this will take more time for sure, because they are not biodegradable per se. So of course, typically it's infinite time. They will just fragment in microplastic, but they won't go for a biodegradation. So that's just something I wanted to point. So now we need to consider, in fact, the biodegradation rate of PHBV or any biodegradable plastic in comparison to another type of conventional plastic. That's something we are going to present tomorrow. And just to conclude, I think this will present the last slide with the results.
Okay. So then just some conclusions regarding the environmental impact on the PHBV packaging. First of all, I've shown you results on the resource footprint, but also for the carbon footprint. The Glopack pellets results are in line with actually other conventionally used pellets. And the technology is still new, so once it will be established and then working for a long time, we are sure that improvements will be possible. But of course, we may not forget, we are stopping here presenting at pellet level. Of course, packaging still need to be produced, and we have heard already some limitations before. So if we would come to a very high mass of tray which is needed, then it means, of course, that the impact of this tray will be higher in Glopack case compared to the other one. But the positive side is that PHBV, in terms when it's, because it's biodegradable, it will be better when it leaks into the marine environment compared to the non-biodegradable plastics. And then regarding in general to the environmental sustainability assessment, we want to highlight that, that the assessment just relies on the quality of the data that is provided. So that's very important. But again gives insight into the hotspot of the production and allows an objective comparison between materials. But not only LCA is important, but we should also have a broader look and have a look to other categories or other impacts as well, as for instance military in this case. Thank you.
Thank you very much, Isabel. Thank you. We have about 5 minutes for some questions. Can I open that up to the audience here, and also those following us on Zoom? They can add their questions in the Zoom chat facility. Yes, just a quick question over there.
Well, yes. I have 2 questions. Firstly, you consider that the highest impact on the production was the energy, followed by the nutrients. So you consider all the energy to produce, or the energy associated as well to produce these nutrients?
No, the energy is really the energy used at the installation itself. So the chemical production or the nutrients production includes the resources needed for this